Hello everyone, we are Group 17. Our project is about image aesthetic and composition assessment. Aesthetic quality is often subjective. However, our goal is to build a machine learning model that can quantify beauty just like a professional photographer. We want our model to distinguish high-quality shots from poor ones, giving a precise score, like 4.4 out of 5 for excellent composition versus 1.8 for a low-quality image. To achieve this, we benchmarked against the state-of-the-art paper, SampNet, which is listed as SampNet hours in this table. While the original paper achieved an SRCC score of 0.65, our optimized model successfully beat this benchmark, achieving an SRCC score of 0.71. We have effectively outperformed the architecture proposed in the original paper. Now, let's move on to the demo. Once the image is uploaded to our website interface, the model processes it in real time. First, you will see the model generates a predicted aesthetic score along with detailed composition attributes. But what truly sets our work apart is interpretability. By applying GradCam technology, we can visualize the model's attention map. As you can see, the red hotspots indicate exactly where the model is focusing. It automatically identified the salient region, the main visual elements of the photo, while ignoring irrelevant background noise. This proves that our model isn't just guessing. It evaluates aesthetic by looking at the image in a way that mimics human perception, making the results both accurate and interpretable.
In this part, I'll explain how we define our problem and our vision. Traditional machine learning assumes an objective ground truth. For example, is this a cat has a single correct answer. In aesthetic machine learning, this assumption breaks down. When people rate beauty, their scores naturally differ. This is what we call the ground truth paradox. So we have to step back and ask a more fundamental question. What is beauty? Plato viewed beauty as an objective, while Kant described it as a subjective universality, personal yet shared across people. Inspired by this tension, our challenge is not to predict a single score, but to learn where images lie on a shared aesthetic spectrum. In this sense, vision has a deeper meaning. It is not just about computer vision, but about what we believe aesthetic AI should learn. Instead of chasing truth, our vision is to model human consensus. We use the CADB dataset, which contains 9,000 images. Although this is relatively small, we were still able to successfully train our model. CADB consists of images rated by 5 expert annotators. We use the distribution of these votes to capture consensus and controversy. The dataset also provides several attributes such as light and symmetry, which help guide the model toward interpretable aesthetic features. For validation, we manually selected 10 pairs of images to check whether the model's prediction align with human intuition. In aesthetic judgment, relative preference matters more than exact scores. Accuracy may be misleading here. Small numerical differences may be ignored when using hard thresholds. Therefore, we evaluate the Spearman's rank correlation, which measures relative ordering rather than absolute values. What matters is not the absolute score, but whether the model understands which image is more aesthetic.
Now I'll quickly summarize what we went through during development. The key idea is every change we made was to better capture how humans judge composition and to improve the ranking quality of our predictions. We began with snap depth from Zhang et al. The main concept is saliency aware, meaning the model tries to focus on visually important regions. It uses a red step backbone to extract features, then applies multi-pattern spatial layout modeling, and finally predicts both the composition score and related attributes together. This baseline gave us a solid starting point, but we wanted stronger global understanding and better ranking behavior. From the baseline, we tried multiple upgrades. First, the original ResNet-based approach had limitations in feature extraction and global context, with SRCT around 0.64. Then we moved to a transformer backbone, SunT, to capture longer range dependencies, and SRCT improved to about 0.67, but training stability was not perfect. After that, we optimized SunT by adding more spatial attention and tuning the loss weights, EMD, attribute loss, and rank loss. bringing SRCC to about 0.6 knot. And finally, our best version used CompNext B2 with GRN to avoid feature collapse, and we broke SRCC to 0.71. For evaluation, we don't rely on just one metric. MSE is the standard regression error between predicted and true mean scores. LCC measures linear correlation between predicted and true scores, but the most important one for us is SRCC. Because aesthetics is relative, we care more about whether the model ranks image A higher than image B, instead of matching an exact score like 4.5. We also use EMD to compare the full predicted score distribution with the true vote distribution, where lower is better.
To achieve optimal performance, we built a four-phase experimental framework. Phase 1 was our baseline. We found that ResNet's small receptive field limited its understanding of global composition, sticking our score at 0.65. In Phase 2, we optimized the backbone using swing transformer. Here, we made a critical change, adding rank loss. Traditional regression only learns absolute score, but rank loss forces the model to learn relative ordering. That image A is better than B. This jumpstart our performance to 0.67. In Phase 3, we optimized the architecture, especially for transformers. We introduced layout query. Instead of passive processing, this learnable vector actively searched the image for composition rule, pushing the score to 0.69. Phase 4 is our final form. We combine the efficiency of ConvNext V2 with our custom SGFN model, which use CLC map to dynamically recalibrate features. This achieved our best LCC to 0.71. To ensure the validity, we conduct an ablation study on 5 key components. Fusion strategy, proving F-line modulation beats simple concatenation. Normalizing choice, verifying GRN prevents feature collapse. Activation function, showing the Lewis regression convergence. Loss weight sensitivity, fine-tuning the rank loss balance. Finally, we use gradient as a lie detector. We reject model that cheats by looking at background noise, ensuring our model focuses on the subject aligning with human vision. In conclusion, our model surpassed the Shanghai Jiao Tong University's SampNet baseline in all metrics, MSE, EMD, SRCC, LCC. We didn't just fine-tune parameter. We continually re-architecture the solution to build the strongest authentic assessment model for this dataset.
Here's our result. Our model can output score distribution and granular attribute prediction. Score distribution is a full probability distribution that let users understand how aesthetic the photo is based on a range, rather than just a single score. And following its granular attribute prediction, it can predict specific composition attributes that the input photo might apply to, so that it can show our score distribution is reliable and provide constructive suggestions. And here's the real-world applications. We think our model can apply to these functions. First is AI photography assistant. It's a real-world composition suggestions in camera apps. And second is aesthetic quality ranking. It can analyze and ranks burst sequence to identify the best shot based on composition quality. And the last one is composition aware reframing. It can crop photos to any target aesthetic ratio while preserving well-composed regions. And our future direction is to transfer learning and expansion. Initially, we used AADB as our dataset. However, we switched to CADB because we wanted to focus more on composition and make the model's judgments more rational. In our future work, we plan to reuse AADB to enable the model to provide more diverse evaluations. Additionally, there are still some unused attributes in CADB that could further enhance our model. We plan to leverage this data to help the model incorporate semantic awareness in the future. And here's our report. Thanks.